Okay, good morning, everyone. We are going to look at uh, structural design of members. So we have started we already completed designing under tension, or how to design tensile members. Then last week we started how to design or how to approach a member which is experiencing bending actions. So now we are going to look at a problem that I have shown you last week, not last week, day before yesterday, to try to work out. So here we have uh, a series of parallel simply supported beams spanning 8 meter and spaced at 4.5 meter centers. They support joists at 750 millimeter centers, which in turn support an ultimate flow action of 7.5 kilopascal. Select the most appropriate UB beam. So designed for bending. Now, when you have a beam which is experiencing forces in the transverse direction, or element which is under action of bending, you might encounter a bending moment, and shear force, and you may also encounter torsion. So we need to check each beam element for bending action, and we need to check for bending moment, whether it can carry the required bending moment, whether it can carry shear force, whether it can carry torsional forces, torsional stresses. So now in this example we have a This is like parallelly spaced beams, and the distance is 4.5 meters. And on top of that, there are joists. So it says you have joists at 750 millimeter centers. So on top of the beam, you have joists. So joists are running perpendicular to the, so this is beam joists. Here the center to center is 750 millimeter. Okay, so then you have a floor which carries a load of 7.1 kilopascal. So example, so the flow applies, the load is 7.1 kilopascal. So Pascal is Newton per meter squared, kilopascal is 7.1 kilonewton per meter squared. Okay, so now we need to design the beam. We need to design the beam. So if you look at the load transfer mechanism, you have a beam like this. Then you have a joist running perpendicular to that. Okay, so then on top of that, you have the sheet. You have the load acting. So on top of the joist, you have a load, flow load acting, that is 7.5 kilonewton per meter square. So if you look at this beam, each beam is spaced at 4.5 meters. So if you so this is beam, this is joist. On top of that, you have a slab. So if you take a middle beam, in the middle, so it will carry this area. So it will carry the load from this area. So if you take a middle beam, the load from this area will be transferred to the middle beam. Okay, so now plus the load of those joists also will be transferred to the beam. So the middle beam carries 4.5 meter with area load plus load or weight of the joists. So now there is no details about the joist here, only the spacing is given here and the ultimate flow action is given here. Okay, so we need to choose appropriate beam. So now what we need to do is we can consider the area load and we will exclude, or we will avoid this joist load because we don't know the joist section, or we can assume a section and then we can provide loads. But at the moment I'm going to assume there is no neglect the self weight. So my assumption here, because since the joist details are not given, we will exclude its self weight. But if it is given, then we have to consider that the weight of the joist as well. But since it is not given here, we will exclude the self weight. So now if we consider the beam, if you consider the beam 4.5 meters, so half of this is 2.25, half of this is 2.25, so 4.5 meter width, and every 1 meter length we can calculate the load. So if you take this one, so 4.5 meter, 1 meter. If you take this load, okay, every 1 meter, so the load is 7.1 kilonewton per meter squared, and if I multiply that by 4.5, I get 7.1 into 4.5, that is 31.95 kilonewton per meter. So every meter, every 1 meter of the beam, we have a load of 31.95 kilonewton. So every one of the beam carries kilonewton load. So that is the load acting on the beam. So the beam is now spanning at 8 meters, right? So according to the question, the beam is spanning 8 meters. So the beam is spanning 8 meters with a load of 31.95 kilonewton per meter load. So that is 8 meters. So now the M, the moment from this load, WL squared by 8. W is 31.95, L squared is 8 squared over 8. So that is 31.95 into 8, 255.6. So 255.6 kilonewton meter is the maximum moment. So the maximum moment on the beam is 255.6 kilonewton meter. We know that critical moment is the MED. So MED is 255.6 kilonewton meter. So now we need to choose a section that is capable of carrying this moment. So to do that, we can try this. Say, if we assume the proposed section is class 1 or class 2, then MED should be less than or equal to MCRD, that is equal to WPL into Fi over gamma m naught. Okay, so that is the equation we obtained from the code. WPL. So the WPL is unknown, and there is no grade is mentioned in this question. Actually, the question should mention the grade as well. So if we assume a grade S355 steel, so Fy is 355, gamma m naught is 1. So that should be greater than or equal to MED. So if you substitute MED value, okay, so substitute MED value, then you can obtain WPL. So to substitute MED value, I'm going to substitute the MED I obtained 255.6 into 10 to the 6, because this 355 in Newton per millimeter squared. So I need to put this into Newton millimeter. WPL into 355 over 1. So WPL should be greater than or equal to 255.6 divided by 355. That is 720 into 10 to the 3 millimeter cube. Okay, 720 into 10 to the 3 millimeter cube, WPL. Okay, so this equation is from here, from this equation for class 1 and 2, WPL Fi into m naught, that is MPL RD. Okay, so WPL should be greater than or equal to 720 into 10 to the 3. So now we need to find the section. So we can say we can find this advanced section stable section properties. So we need to pick a WPL value greater than 720. That is plastic section modulus. So here you can see the dimensions, and then let's go down. Okay, let's go to the bottom. So here we are getting the 123 centimeter cube. So we need 720. Let's keep going up. 720. Here there's what first 720, but it is 720. We will prefer something greater than 720. So 846 is one option. So you can have possible sections. Three zero five 165 into 54. That has a WPL value of 834. So 846. So this is 720 10 to the 3 millimeter cube means 720 centimeter cube. So this is one option, satisfies. But we should not, settle with the first option. We need to see whether is there any lightweight ones. Okay, there is another one, 775, which is 356 171 45. 356 171 45. So that is another option, 770. So that has a another option is 724 here. That is 406 140 39. WPL 724 centimeter cube. So we have three choices. In these three choices, obviously our selection will be the lightweight. So whichever gives us the lighter weight, we will choose that. So among these three, this is the most lightweight. This is about, say, 39 kilogram per meter. This is 45 kilogram per meter. This is 54 kilogram per meter. Since we require something satisfies 720 centimeter cube, we can take 724 centimeter cube. So therefore, we select the lightest of three, that is 406 into 140 into 39 UB. Now we need to see, now for example, we assume 355 steel and we have substitute 355, so we need to see whether it satisfies. And also it should satisfy the classification. So now we need to see the classification. So if you take 406, I have shown you how to do the classification, so I'm going to take the value from here. Say, if you take the web, okay, so if you take the web, 406, if you take the web, it is 56.3. So web CW over TW is 56.3. Flange outstand, we have 6.69. CF over TF 6.69. And we need to find our Fy value, okay? Fy. So Fy is, we have to see the thickness of the flange and thickness of the web. So thickness of the flange is 6.4 millimeter, thickness of the flange is 8.6 millimeter, web is 6.4 millimeter. Both are less than 16 millimeter. So safely our Fy is 355, since thickness of the web is equal to 6.4 millimeter and thickness of the flange is equal to 8.6 millimeter. So here these values can be obtained. Here Fy is 355 Newton per millimeter squared. So if Fy is 355 meters squared, we can obtain the classification from the Eurocode. Table 5.1, 5.2. 5.21, this is for the web. So your epsilon is 0.81. So epsilon is 0.81. So we can find, excuse me. Now, to be class 1, CW over TW should be less than or equal to 72 epsilon. So to be class 1, CW over TW less than or equal to 72 epsilon. So 72 epsilon is equal to 72 into 0.81, that is 58.32. So our web satisfies. So 56.3 less than or equal to 58.32, that is correct. So web is class 1. Then flange CF over TF. So the flange should satisfy the table 5.22, flange outstand. So it should satisfy 9 epsilon. So 9 epsilon is 9 into 0.81, 7.29. 9 epsilon. So our CF over TF is 6.69. So 6.69 less than or equal to 7.29 satisfies. So flange is class 1. Therefore, the overall section is class 1. Hence, the section we have proposed for this beam, the section we have proposed is 406, 140, 39. Okay, 406, 140, 39. This is the section. Therefore, UB satisfies design requirement. So now if you can see here, we have chosen a section. We have chosen a section based on two assumptions. One is our steel yield strength is 355 and the section is either class 1 or class 2. That's why we use this equation. So those two assumptions must be proved at the end. So that's why once we have chosen this section, we have checked for class and we proved it's class 1, and also based on the thickness of the web and flange, we proved that the yield stress is 355. So both my assumptions are correct. So the section I considered is correct. Suppose if we choose a section and then if my assumptions becomes wrong, then I have to redo the whole thing with a different section. Okay, for example, while doing this one, if I get my Fi to be 335 because of the thickness of the element, if it is reduced to 335, then I have to redo the whole thing. That is for bending check. Now we can do the shear check as well. Okay, so we have seen how to do the shear pull. So we'll do the shear check also. Now this beam, this is the beam 31.95. Okay, so the beam applied with the 95 kilonewton per meter. So then your shear force diagram is going to be like this. So what is this maximum shear? That is equal to the support reaction. So 31.95 into 8, 127.8. 8 meters. So if you consider the shear check, so VED should be less than or equal to VCRD. This is a shear check, clause 6.2.6. So VED, VCRD. So now what is a VED? That is a critical shear force, 127.8 kilonewton. So VCRD should be greater than or equal to 127 kilonewton. So what is VCRD? The code says VCRD is equal to VPLRD when you can develop plastic shear resistance. So plastic design VCRD is the design plastic shear resistance as given in clause 2. So for elastic it is VCRD. So VPLRD is, so VCRD, VPLRD, that is equal to AV into Fi over root 3 over gamma m naught. So AV Fy over root 3. Now AV into Fy over root 3 gamma m naught should be greater than or equal to 127 kilonewton. So AV and Fy is 355 Newton per millimeter squared. This is 1. 127 into 10 to the 3 Newton. So now 127 into divided by that is AB greater than or equal to 619.64 millimeters squared. So the area should be greater than 619.64 millimeters squared. So that is a required area to satisfy the shear requirement of the load. Now we have already chosen a section for bending, so we have to see whether that section satisfies. So 406, 140, 39. So so AV is obtained from this equation. Okay, so AV for rolled I and H sections, load parallel to the web. So if you take the I beam that we are loading, so this is how the beam is, and the loading is like this. Loading is parallel to the web. So since that is the case, we have to choose this equation, that is AV is equal to A minus 2BTF. So AV is equal to A minus 2BTF plus TW plus 2R into TF. So this is the equation. So A is, so if you take the I section, day before yesterday I told you, take the I section, A is the gross area. So A is the gross area. Gross area is, for that section, gross area is 49.7 centimeters squared. 49.7 centimeters squared. So, excuse me. Centimeter squared, I can convert it to millimeter, minus 2 BTF. 2 BTF, this is B. This is TF. So 2 BTF. So we subtract both flange areas. So B is, we have to obtain from this table, B is 141.8. Okay, so 141.8 B. 2 into 141.8 into TF. Thickness of the flange. Thickness of the flange is 8.6. Plus, so you remove this area, so means you get only the web area. You add TW plus 2TR. TW is this thickness of the web, TW. 2TR is the 2 root radius. So basically you add this area to that. So this is the shear area, the highlighted one. TW, what is TW? 6.4 millimeter. 2R, what is R? Root radius 10.2, 2 into 10.2, 20.4. TF, thickness of the flange, that is 8.6. Okay, so now what is this area, AV? That is 4,970 minus 2 into 141.8 into 8.6. That is 2,438.96 plus 6.4 plus 20.4, that is 26.8 into 8.6, that is 230.48. So 4970 minus 2438.96 plus 230.48. So AV is now 2761.52 millimeter square. So 2761.52 millimeter square is for the section we have chosen. So for 406 into 140.39 here, 406 140.39 UB. AV is 2761.52. That is greater than or equal to 619.64 millimeters square. Therefore, the section satisfies shear requirement. Now, not only shear, now in this being both shear force and bending moment act together, so we need to see the combined effect. So if you look at the code, bending and shear, clause 6.2.8, bending and shear. Where the shear force is present, allowance should be made for its effect on the moment resistance. So if you have both shear force and bending moment acting together, you need to give provision for the you should make allowance for the shear force. So in that case, if you look at the second clause, that is so the clause 2, where the shear force is less than half the plastic shear resistance, its effect so where the shear force less than half the plastic shear resistance, its effect on the moment resistance may be neglected except where shear buckling reduces the section resistance. Now we have to check this one before we move to this clause 3. In our case, when you have both shear and bending, you need to check for the influence of shear on the bending resistance. Suppose if the shear force is less than half the plastic shear resistance, its effect on the moment resistance may be neglected. Third, otherwise, if it is not less than half, then you have to find the reduced moment capacity using this equation. Okay. So now, if the close to not satisfied for our beam, we will be in a bit of a trouble. You know why? Because we will be facing an issue where our FR will get reduced, and because we have chosen a section that is marginally better than the required, so we might fail moment resistance. So that is a bit of a danger we have. So because we require 720 720 centimeter cube section modulus, we have chosen 724. Now that means compared to the required moment of 255.6 kilonewton meter, our section may be having a little bit more than that. So that's a bit of a danger, because if this close to is not satisfied, our moment capacity will be reduced by this ratio. So in that case, what we need to do is we need to see whether this section is capable to carry the moment. So let's check the close to plastic shear resistance. If we can find the plastic shear resistance. So what is the plastic shear resistance? VPL RD is equal to this, AV into Fi over root 3 gamma m naught. So AV is 2761.52, 355 over root 3. So what is our plastic shear resistance? 2761.52 into 355 divided by root 3. Is divided by root 3. 2761.52 that is 566 kilonewton. So plastic shear resistance is 566.02. So our actual shear force is 127.8. So 127.8, twice of that. So the clause says the shear force is less than half the plastic shear resistance. Its effect on the moment resistance may be neglected, except where shear buckling reduces the section resistance. So shear buckling is another thing, another behavior we need to check. Now if 127 kilonewton, that is a 27.8. Okay, if 127.8 less than half into 566.02, then we can neglect effect on the moment resistance. Influence of shear stresses on the moment resistance. So what is half into 566? So 56602, that is 283.01. So 127.8 less than or equal to 283.01. So that is correct. Therefore, it is not required to reduce the moment resistance. So therefore it is not required to reduce the moment resistance. So now we can see that we have checked for bending, then we have chosen a section that satisfies the required bending based on the lightweight option. Then we have validated that it is either class 1 or 2 and it has a yield stress that we assumed to select the appropriate section. After validating it, we confirmed that the section is capable to carry the required moment. So then we checked for shear. We calculated shear force and we have calculated the shear area, and we have checked for combined shear and bending moment resistance. Actually speaking, the combined shear and moment, now for example, if although we have checked 127, we have to check only maybe something less than that. For example, your bending moment diagram is like this: 255.6 kilonewton meter. That's right. Yeah. And our shear force diagram is this: 127.8 kilonewton. BMD SFD. Now, if you take the combined, if you take in the midspan, the combination is 255 and 0. If you take the combination of the support, is 127.8 and 0. So therefore, if you take the combined action, the maximum combined action is occurring somewhere in between these two, because here there is only pure bending, no shear. Here only shear at the support, no bending. So the combined is occurring in between these two. So in generally, if you check these two conditions, extreme cases, if they satisfy, then the remaining areas will satisfy. Okay, so now we have checked bending, shear, as well as bending and shear. And suppose if you have bending, shear and axial force, say for example, if you look at this 6.2.9 is bending and axial. We have seen that shear capacity, bending and shear, bending, shear and axial. Now, in members where you have bending and axial force occurring, you have to check the influence of them. So, for example, if for the class 1 and 2 cross section, now in our problem here we don't have axial force, but in some cases you might have some axial force. So in such case we need to look at how to approach it. Okay, so now how to approach it? If you look at the close, where an axial force is present, allowance should be made for its effect on the plastic moment resistance. For class 1 and 2, the following criterion shall be satisfied. That is, MED should be less than or equal to MNRD. Okay, so bending plus axial. So when you have these two forces acting, so when you have axial force will be acting along its entire length. So you might have the effect of these both. So in such case, your MED should be less than or equal to MNRD. MED. Note that if it is a pure bending, we consider MCRD, but it is now MNRD. So MNRD is obtained from this equation, that is, for a rectangular solid section without fastener holes, this is MNRD. For a rectangular solid section, so it's like a solid rectangular beam. Our I section is not rectangular. For double symmetrical I and H section or other flange sections, allowance need not be made for the effect of the axial force on the plastic resistance moment about the y-axis when both these criteria are satisfied. So for I and H sections, doubly symmetrical, this is the I section, this is the y-axis. Okay, so allowance need not be made if they satisfy these criteria. So if your NED less than or equal to 0.25 NPL RD, that is, if your axial force is less than 25% of the plastic resistance plus your axial force, that is design effect, is less than or equal to half that web capacity, then you don't need to consider the influence or the effect of axial force on the moment resistance. If it is about z-axis, you don't need to consider the reduction or the effect of axial force on the bending resistance if it is satisfies this. So you have to check these clauses. For cross sections where fastener holes are not to be accounted for, the following approximation may be used for standard rolled I section and H section and for welded I sections and H sections with equal angles. So your MNYRD is obtained from MPLYRD into 1 minus n over 1 minus 0.58. So your MPLRD is what we normally obtain, and you have to multiply by a factor here. That factor is obtained from these equations. What is N? N is NED over NPLRD. What is A? A is equal to A minus 2BTR over gross area. So if you consider these two N and A values, okay, if it does not satisfy this, if it does not satisfy this case, then you have to reduce the moment capacity. So the reduced moment capacity MNRD by y-axis is obtained from this equation. Okay, so MNZD by z-axis obtained from this equation. So these these checks you need to make when it comes to bending plus axial forces acting on a member. Okay, so that is the check for bending plus axial and bending plus shear. Then you have bending, shear and axial. So where shear and axial force are present, allowance should be made for the effect of both shear force and axial force on the resistance. So this is the next clause on this bending 6.2.10. When you have all three, bending, shear, axial forces, then you have to reduce the bending capacity based on the axial and shear force. Provided that the design value of the shear force VED does not exceed 50% of the design plastic resistance, no reduction of the resistance defined for bending and axial force in 6.29 need be made except where shear buckling reduces. So if your VED is less than half the VPLRD, you don't need to worry about that combined action. Where VED exceeds 50%, then you have to use this equation to calculate the revised yield strength so that you can obtain the revised bending capacity. So that is about bending, shear, bending plus shear, and bending plus axial, and bending plus shear plus axial. So now you know how to approach all the members which are all the beams which are under the action of bending. So you can able to design all the beams uh, using the uh, knowledge that you have gained now. So we will go to the next area, that is buckling. Before going to buckling, I think we have to check the compression. We have seen tension, but we have not looked at compression. Members under bending, tension members. We have completed the tension members. Shear, Let us see the code. So we have if you look at the ultimate limit state, the 6.2 is resistance of the cross sections. We have seen this. Six point 6.2.3 tensile members, 6.2.4 compression members. Okay. So when designing compression, so like the tensile members, your NED less than or equal to NCRD. Earlier it's NTRD for tension, compression NCRD. So design resistance to the cross section for uniform compression NCRD should be determined as follows. So NCRD is equal to A into Fi over gamma m naught for A into Fi gamma m naught for classes 1, 2, and 3. So NCRD is equal to A effective into Fi over gamma m naught for class 4. Class 4. That's it. So we'll see the details of that. Fastener holes except oversized and slotted holes defined in EN 1990 need not be allowed for compression. So if you have a fastener hole and if the fastener hole is filled, then you don't need to worry about the area reduction for the fastener holes when it comes to the compression members. In the case of unsymmetrical class 4 sections, the method given in 6.2.9.3 should be used to allow for the additional moment delta MED due to eccentricity. So that is a check. So for example, if it is under bending, you have to check for design resistance according to the clause. But compression is not as simple as you think. So there are different kinds of compression failures could occur. So we will see that. Okay. So when it comes to the compression, you have to consider the following part of the clause. That is where you anticipate a buckling. Okay, so this should be combined with compression members, that is 6.3 buckling resistance of members. So these are the general equation if they are purely under compression, but buckling resistance compression members also should be checked. So how to do this? How to do the check? Now, if you have a member which is under compression, there are two possibilities. Okay, so the member under compression, either it can crush so member under compression. One option can have local buckling. Second option can have global buckling. So those global buckling means when you have a member, when you apply a compressive force, it buckles like this. So global buckling. So we need to see which capacity is the lowest, whether the global buckling or crushing. Through compression, it can get crushed or it can fail by material failure, or it can fail by buckling failure. How to check the buckling failure? So you have to, when there's a compression member, you have to check this one also. NED should be less than NBRD. So you need to check, you need to obtain for any member under compression, you need to obtain NCRD and NBRD. The lowest, the two will determine, will dictate the failure mode and capacity. Okay, so you need to obtain these two. NCRD you can obtain very easily from these equations. You get the gross area in the Fi over gamma m naught for class 1 and 2 and 3. A effective in the Fi over gamma m naught for class 4. But NBRD obtained from design buckling resistance. For unsymmetric members, you will have additional eccentric moment as well. So the design buckling resistance of compression members should be taken as so design buckling resistance of compression members can be obtained from these two equations. NBRD this is called she into A into Fy over gamma m naught for classes 1, 2, and 3. So you know that we know this one. This is NCRD. You multiply by she. That is the NBRD. So again, NBRD is she into A effective Fy gamma m naught for class 4. Okay, so how to find the she value? She is the reduction factor for the relevant buckling mode. So she is the reduction factor for relevant buckling mode. These two are same almost. That is, compression buckling and lateral torsional buckling are kind of similar. So she. So the she is the reduction factor for the relevant buckling mode. For determining the buckling of the members with top sections, tapered sections along the member or for non-uniform cross sections, we need to do the second order analysis. This part is not relevant to us at this moment. So in determining A effective, the holes for fasteners at column ends need not be taken into account. So when designing A effective for the class 4, you don't need to consider the fastener holes at the end of the beam. So the she value is obtained from this buckling curves. She is from this equation you can obtain. She is always less than or equal to 1, because if it is 1, then it is similar to the compression capacity. If it is less than 1, it is the buckling capacity. So she is obtained from this equation, where you can see the psi in this equation is defined by this, and then the lambda bar is defined by this. So the lambda bar is the two different lambda bars, that is lambda bar is A into Fi over NCR, and here lambda bar A effective into Fi over NCR for class 4. So if you look at here, we know A, we know Fy, we don't know NCR. What is NCR? NCR is critical axial load. Actually, critical buckling load, you know that critical buckling load, you know how to obtain it. And we can see that there are different curves. And this curve can also be used to obtain these ABCD values. So this is something else. This is for flexural buckling. So here, we need to obtain the she value. She value is depending on the psi and lambda bar. Psi is obtained from this equation, and lambda bar is obtained from this equation, where NCR is the elastic critical force for the relevant buckling mode based on the gross cross-sectional properties. NCR is the critical buckling load. So you have heard of this critical buckling load before, and you can recall it. Here we have the critical bending. So critical buckling load is from the buckling of struts sections that you might have learned. From the buckling of struts, you can obtain NCR. Once you obtain NCR, you can get lambda bar. Based on lambda bar, you can obtain the, if you go to this chart, okay, so if you go to the chart, say the reduction factor for relevant lambda bar can be obtained approximately using this chart. If you know this, which curve should refer. So which curve should you refer is given here. Selection of buckling curve for a cross section. So here, if you look at an I section, roll section, if your H over B ratio is greater than 1.2, you have to refer these two. If your H over B ratio, that is the breadth over, or the height of the breadth, is greater than, less than or equal to 1.2, then based on the thickness of the flange, you can choose the curve. So it's very easy to choose the curve. Once you have chosen the curve, if you know the lambda, you can obtain approximately the reduction factor. Otherwise, if you know the if you know the curve, you can obtain the alpha value from here. So using alpha and lambda bar, you can obtain psi. From psi, you can obtain chi from these equations. Okay. So when we meet next Monday, we'll work out a problem on compression members. So we have done a problem for bending in detail, but when we EN 199311, you can easily download it if you search it, because I think it is a the copy that I have is not a legal copy, so I can't upload legally. So there can be some legal consequences. But if you search on the Google, you can download it. Okay, that's for sure. Or you can buy from Sri Lanka Standards Institution a hard copy for a minimal price. Okay, something 200-300 rupees. So that is there. So unfortunately, I can't upload to the course web. So if any of you come and see me, I can give a copy in a pen drive. Okay, that is possible, but I can't upload to the course web. When we meet on next Monday, we will look for one example, a comprehensive example for the compression member. Okay, so we'll stop here and I'll meet you again next Monday.